Swayam Prabha. Digital India. Educated India.
We have seen the octahedral complexes, we have seen the tetrahedral complexes. These are the two most important classes of compounds that are present over the, let's say, whatever chemistry known so far. There are other complexes, as you have seen, it could be, pentacoordinated. The metal complex can be pentacoordinated. Two different types of geometry is possible for pentacoordination. Out of that, trigonal bipyramidal is one of the preferred geometry. So there are a lot of things that we can definitely go on and discuss about it, but it's literally impossible to discuss each and every structure in detail, each and every metal complex kind of different geometry in detail, and how their ligand field will affect the d orbital splitting. So geometry changes, d orbital splitting pattern changes. I think just by learning octahedral and tetrahedral, you have got that sense. Now it has all to do with the way the ligand is approaching. Sometimes ligand is approaching directly towards the atomic orbital of each of those metal or d orbital of the metals, and thereby you can see the extent to which it gets stabilized or destabilized is differing, right. So if you take, technically speaking, if you take a trigonal bipyramidal, perhaps you would be able to at least understand why the splitting is such that. Okay. In the syllabus, for you guys, we do not have any other geometry to discuss, octahedral and tetrahedral. If possible, you can look at little bit at trigonal bipyramidal, TBP. Okay. Now square pyramidal or square planar is something which will come soon. Square planar is basically nothing but octahedral geometry you are having. You take out two z axis. You have octahedral scenario, you take out two z axis. That's become square planar. So we will discuss that. So in the last class, once again, we were discussing Warner coordination theory, 18 electron rule, valence bond theory, and how good it is, and then how bad it is, and how good the crystal field theory is. Really, we will stop there, how good the crystal field theory is, and not too much we will get into the MO approach, molecular orbital approach. Okay? There are, no end to learning. I think for this course purpose, we will stop in there, not too much afterwards. Okay? So the major objective for this syllabus or for this chapter and the next chapter is definitely giving you an idea about these high spin, low spin complexes, the spectrochemical series. I hope you have come across this term in the last class, crystal field stabilization energy, Jahn-Taylor distortion and spinel. These are the last two topics we will discuss today. I will briefly give you an overview what we have discussed in the last class. So this is an octahedral complex, metal center is there at the middle of it. So that is at the center of the geometry. It's a metal center. Metal and ligand are almost having electrostatic interaction. It's a positive charge and negative charge are the ligand which are interacting with the metal center. Remember, in the valence bond theory, we were mainly assuming it's a covalent structure. Okay. As you see, this is axial position, that is also axial position. This is the direction where dz2 orbital is, dz square or dz2. Now these are the direction, these four, 1, 2, 3, 4. These four are the ones where we have dx2, dy2 orbital directly. It's not indirect. This is where is actually dx2, y2. So therefore, from this you can understand why dz2 and dx2y2 orbital is most destabilized for octahedral geometry, because they are the one which facing the music basically. They are the one which is getting repelled most, because ligand electrons and the d orbital electrons are repelling each other. Very simple. Now all other orbitals dxy, dyz, dxz, they are not facing these ligands directly. They are in between, somewhere here, 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 so in between. So thereby they are not going to get repelled too much. They are going to get repelled but not too much. Okay? Relative to dx2, y2 and dz2, they are going to stabilize. Okay? So just a quick look at the orbitals, what we have discussed in the last class: dz2 orbital, dx2, y2 orbital. Okay? Now these are the other orbitals. With respect to these three other orbitals, you can see where the ligands are. Therefore, you can understand the stabilization or the destabilization of these. Okay. Yeah, that's a good question. Usually, that is where we will come to Yann-Taylor distortion. Okay. That I guess that you will be able to clearly understand when we are discussing the Yann-Taylor distortion. That is actually the origin of Yann-Taylor distortion and Z elongation and Z in. Okay, we'll come back. Now this is the same thing in a different bottle. I think whatever fits you, you just look at it. It gives you a very clear idea. These are the ligands. The black balls are the ligands, and the metal orbitals or d orbitals are shown in here clearly. Okay, no confusion, right? Now as we were showing in the last class, so these are d orbitals and this is, let's say, ligand electrons. Ligand electrons are coming for these orbitals to overlap, right? Now first instance we will discuss the dz2 interaction with the ligand. Ligand electrons comes, they will be repelling each other, therefore dz2 will be destabilized. dz2 is facing the ligand once again directly. This is the dx2 y2 one. Okay. Now here you see that the four ligands are coming along all these axes. To answer to that previous question, one of the way you can see is these are four lobes divided by four ligands and two lobes divided by two ligands. Kind of that's how perhaps it's, you don't have to worry usually. But finer details, when it is unsymmetrically filled, right, dz2 and dx2, although they are of same energy, but if they are unsymmetrically filled, let's say 1 is there in the Eg orbital or 3 is there in the Eg orbital, then the problem comes. Okay. Now, so you have seen how they are coming, and thereby they are also getting, these orbitals are getting destabilized. Okay. All other d orbital, like these three are like dxy, dxz and dyz, they are really not facing the orbitals directly. As you can see, they are sitting right in between, and thereby you can see, so for example over here we have shown dxz, same is true for dxy and dyz. Thereby these orbitals are relatively, mind you, relatively stabilized with respect to dz2 and dx2y2. If you compare the free metal ion, with respect to free metal ion, everything is destabilized, because free metal ion has no ligand, thereby no repulsion. The moment ligand comes, repulsion starts, so the system's energy goes up. Okay. Now overall, therefore, you have 2 up, 3 down. Okay. But net stabilization with respect to that barycenter, the center in the middle, the net stabilization or destabilization for a completely filled d orbital, let's say d10 or d5 in a high spin situation, which we have discussed, should be the 0. Stabilization, if it is completely filled, total stabilization and total destabilization has to be the same. Okay. Now this is where, again, once again, this is kind of a clear picture. This is a octahedral field we were showing, 6 ligands coming at this box. So if you are assuming that this is a box, 6 ligands are facing the way it is shown, 1, 2, 3, 4, 5, 6. Now this is the free metal ion, this is the metal complex, 3 of the T2G got stabilized, 2 of the EG got destabilized. Okay. Now this is EG, not E. E will be for tetrahedral, T2G, not T2. Okay. Now, of course, I think I have discussed this information already. Now, since this is 3 of them, this is 2 of them, this distance between this barycenter and the stabilization for T2G, yeah. Ligand may be different, yeah. Here we are thinking, see, we have to deal with the idealistic world at the beginning. ML6, ligands are same, ML6. We are not thinking like 3 of the chloride, 3 of the fluoride, that's a mixed situation. Okay. For just to of course, those situation often comes, but this is, if we don't understand, I mean, very simple situation, how can we go complex? Okay. So, of course, let's say if you have 3 chloride and 3 cyanide, what will be the situation, right? That is a special, topic on this. How finer details you can get in the d orbital splitting. Initially it may split and then they may further split. If you have all of them, let's say weak field, like 3 fluoride and let's say 3 chloride, they may be behaving same. But the moment you have one weak field, one strong field ligand, things will be little bit complicated. Okay. So overall, how much ligand, I think overall you have to see whether it is a strong field ligand or weak field ligand, whether it's a first point, whether it's a octahedral geometry or tetrahedral geometry, and thereby go for it. For the exam purpose for this course, I don't think we will be tricking into anything which is mixed, little bit more complicated than that. For exam purpose or for this course purpose, you have to just know octahedral field splitting and tetrahedral, and we will be discussing briefly about the square planar, because that is kind of comes automatically. Furthermore, if you want to learn, maximum go to trigonal bipyramidal. Okay, we will give those splitting, but as again, it's a more complex than we would like to think. We are just dealing idealistically. Okay, that's a good question. So over here we see that this stabilization should be 0.4, 2 by 5 delta 0, 0.4 delta 0, this destabilization would be 0.6 delta 0. We have discussed it, or 4 dq, 6 dq, if it is delta 0 or 10 dq, we have discussed, right? Now, the first advantage of this crystal field theory is you can explain the magnetic properties, you can expect to explain the spectroscopic behavior. Let's say UVB study, why certain peaks are coming. So this is where we were telling that if you have an unpaired electron, if you are moving from T2G to EG, the spectra you get will be something like this, absorption maximum. Of course, we are not getting into finer details of the spectra, but this is the major origin where from electrons are moving and where it is going. So from T2G, this is a D1 electronic configuration, 1 electron is there. So T2G1, that means over here, T2G1, 1 electron was over here, all these 3 orbitals are degenerate, same energy, only way it can go is up to here. Now if you think, if EG is splitted further, these 2 orbitals are dx2, y2 and dz2. If it is splitted further, so the electron can go to 2 different levels, right? Therefore, you can expect 2 different peaks Whether intensity will be high or low, that is, of course, then you have to think about the symmetry and lot of other things which we will not be discussing. But you can sense where the spectra is coming from and where the electron is, moving from, which orbital to where it is going. Okay, so this is fine. So you get the spectra. Now we have also seen crystal field stabilization energy. So you calculate, you are given, I think you have to really master this. You should be able to do it in your dream. Okay. D3 electronic configuration. What is the crystal field stabilization energy if octahedral? D5, what is, if it is octahedral, how many scenarios are there? 2 scenarios, high spin and low spin, right? So what will be the crystal field stabilization energy? Any question, especially in exam, if you see, before even thinking too much, I would say, just imagine the scenarios. Only 3 scenarios you have. Octahedral 2 scenario, high spin, low spin, and tetrahedral, only high spin scenario. 99% case. We'll discuss one case today which is otherwise, but that's it. Octahedral 2 scenario and tetrahedral 1 scenario, done. So once you have that, I think the answer should come out almost, like why something is preferred, why something is not preferred. At least I would say out of 25 mark question, 5 marks to 7 marks will be based on that indirectly. Of course, it will not be given perhaps on a platter. Definitely you will be able to figure out that. So please do familiar. You should not be fearing about calculating, and electronic configuration should be always correct. There should not be any mistake. Okay. Now, so D5 system, for example, one case we were giving. So this is the D5 high spin. That means 3 stabilization, 2 destabilization. CFSE should be 0, right? That's what I was trying to say. So net stabilization and destabilization should be 0 if it is symmetrically filled. Okay, so this is 0. You don't have to even calculate. If it is D10, it is again 0. D10 means all of them are full. So stabilization is equals to destabilization. So that is where, let's say you are given D7 and this is the configuration. 5, 6, 7. So 5, take out 5 because 3 plus 2 has stabilized, destabilized and cancel each other out. Now you just deal with 2. 2 will be D7, 2 will be over here and here, right? So that will be minus 8 DQ or 0.8 delta 0 or delta octahedral. You should be able to do it really, really quick without calculating and going through the simple math. Now, of course, D7 you can have also high spin and low spin configuration. For example, this one, what would be the CFSE? Minus so of course minus, that is out of question. It's stabilization. Each of them are 0.4. So 5 of them 20 minus 20 or minus 2 minus 2 delta 0. Okay, that's it. Delta 0 means delta octahedral, delta O, different people pronounce it different way. Okay, so this is it. If you do it really simply, I'm sure 5 to 7 mark question will be there. Invariably, whatever it is, the question is based on that. It's going to be based on that. Now, of course, we have discussed it. Once again, 2 scenarios. High spin because the spin is maximum, high spin. Low spin means spin is minimum. You see 1 unpaired spin. Now, if you look at I will come back to the magnetic behavior. Magnetic behavior is nothing but due to the unpaired electron, right? So the moment you have unpaired electrons, magnetic behavior comes because the parallel spin will cancel each other. You want to spin on that direction and I want to spin on this direction, so it will be cancelling. So this is the one will have low magnetic value, magnetic moment value. This is the one will have high magnetic value. This is the origin for molecular magnet. A lot of molecules are magnet. Okay, And these are the ones you see the application almost everywhere, literally everywhere. You take any electronic gadgets, you take almost anything which is electronic in nature, which has some fancy application, it is the material. It is the material which are having magnetic properties, and that is why they are used. How expensive it is, based on that, you will get your material. Of course, in lot of other cases you see the use of these things. I will show one or two cases today. Okay. So dependence of delta 0, like how much splitting is going on, that depends on the nature of the ligands, as I was trying to tell you, whether it is a weak field ligand or strong field ligand. Strong field means the splitting will be very high. Weak field means the splitting between T2G and EG will be small. And therefore, for weak field ones, we will always see high spin, means spin will not be pairing up. Okay? And the charge on the metal, of course, if it is a higher charge, you will have higher separation. If it is 5D, you will have higher separation compared to 3D, right? So this is the spectro-electrochemical series with respect to different ligands. These are the stronger ones, stronger ligands. These are the ones which almost always will give you the low spin, which one? Low spin complex, because the splitting will be high. Strong field ligand, splitting will be high, so the spin pairing will happen. It cannot go from T2G to EG. Okay? These are the ones which are likely to give you low spin complexes. Is it getting clear? If it is, you are getting, sometimes it is little bit confusing. It is either yes or no type of answer question. The understanding is either yes or no, high spin or low spin, right? So just get it clear. Now this is the trend we have shown. For tetrahedral case, we were dealing with a completely different scenario which can be clearer from this picture. If you remember the previous picture for octahedral case, which was nothing but direct confrontation, here it is like more of a political approach, okay? Diplomatic approach. You do not go direct, you just talk with, okay? So they are talking, and they are not directly confronting, thereby the scenarios are completely different, since it's not interacting directly, overlapping directly with, let's say, those EG orbitals. Previously we have seen for octahedral cases, dx2y2 and dz2. dz2 is over here actually, and see the ligand where it is. Ligand is here, dz2 is here. Actually those orbitals are the ones, those EG orbital for octahedral case are the ones which are farthest from the ligand, which are farthest, and thereby they are the one which will get stabilized. The other three orbitals, dxy, dyz, dxz, those are the ones which are nearer, not directly overlapping but closer, and thereby they are destabilized. Okay. Now this difference is called delta T, and this delta T is going to be 4/9 of the delta O or delta 0. 2/3 coming from the number of ligands, 6 to 4, octahedral to tetrahedral, another 2/3 coming from indirect approach, not from direct approach. If it was directly approaching, that is the case of octahedral case, but here indirect approach, basically you can calculate based on the angle, which angle it is coming. Okay. So roughly these are like rough calculation, it is becoming 2/3 times 2/3, 4/9 of delta 0. So delta T is always less, therefore you never see, almost never ever see low spin case for tetrahedral. Since the splitting is very less, always you end up getting high spin case. So never ever calculate tetrahedral for low spin. Now this is the electronic configuration and their respective stability if you are comparing delta octahedral and delta tetrahedral directly. So what happens, how much stability is there if it is D1 for octahedral case, D1 for tetrahedral case, and we are comparing apple versus apple. That means high spin versus high spin of octahedral and high spin of tetrahedral. Tetrahedral cannot have low spin. In tetrahedral case, we have to normalize the value with the 4,9 of delta 0. These two. You do it, you will get this. You should be able to get it. Okay.